Math 110, this is going to be review number 2. So we're going to start with just-in-time number 18, and this is simplifying rational expressions. Now there's a few elements that we have to examine when we're simplifying rational expressions. First is going to be the domain, and that's going to be the set of the numbers where the expression is defined. So typically when we're dealt with a rational expression, which is going to be the quotient of two polynomials, we want to often find what the domain is, because then we can see maybe some exclusions, or it could be some pieces of information from the graph that may help us find other pieces of information. So finding the domain of the graph, one of the restrictions of a domain is that you cannot divide by 0. Okay, that's going to give you an undefined value, and the domain is where my expression is defined. So you can probably see the contrast there. So one of the ways that we can do that is we find where x is undefined, and so I could set my denominator equal to 0. Now if I set my denominator equal to 0, one of those ways that, or the tools that we have to be able to find those values, is going to be the factoring, and so that's what I did here. If I took this and I factored it into this statement using that little x method and the factor by grouping, if I set each of these equal to 0, x minus 5 equals 0 and x plus 1 equal to 0, and I'll write that out for you. So we say x minus 5 cannot equal to 0 and x plus 1 cannot equal to 0. Well, if I add 5 to both sides, I get x can't equal 5. If I subtract 1 from both sides, I get x can't equal negative 1. And those are going to be the values that would set my denominator to equal to 0. So what I can do now is I can create a number line, and on this number line, if I say what x can't be, and so in this case I said it can't be negative 1, and I said it can't be positive 5, but I didn't say it can't be anything else. And so I can make the assumption that x is going to be everything else, and so that's why everything else would be shaded. And so from here, we can write this as interval notation. And so I can say from negative infinity all the way to negative 1, union from negative 1 all the way to 5, union from 5 all the way to positive infinity. And this right here is going to be the domain of my rational expression. So on this one, we can simplify and state the domain of this. Now, one thing to kind of point out, when we're trying to simplify, you can only simplify factors. Now, when I use that word factors, okay, factors implies multiplication. So just know that what we're going to be doing is we're going to be factoring this equation to be able to find what simplifies. So let's just find the domain first. I take the bottom, says it can't equal to 0. So solving for it, add 12 to both sides. I get 12x squared equals 12. Divide both sides by 12. I get x squared equals 1. Square root both sides. X can't equal plus or minus 1. So on the number line, it can't be negative 1, can't be positive 1, but I didn't say it can't be anything else, so everything else is shaded in. And so my interval notation, negative infinity to negative 1, union negative 1 to positive 1, union positive 1 to positive infinity. And this right here is going to be the expression of my domain. But now I need to simplify this. So in simplifying this, like I said, I need to find what those factors are. And so in this case, on the top here, I found what my common factors are going to be. And so what I was able to do is I said, well, there's a 3 in common on top, and there's a 12 in common on the bottom, so I did that. Then to factor this statement, if I do that x box method, or I create that x and, do the whole factor by grouping thing, then it factors into this statement here. And then this is the difference of squares, and so that factors into this statement here. And so now we have to look at what are common factors that cancel out. And so in this case, x plus 1 and x plus 1 cancel out. There's a common factor of 3 between 3 and 12. So there's a 1 left over here, and there's a 4 left over here. And so there's nothing else. So my answer is going to be 3x minus 1 over 4 times x minus 1. And that's going to be my result. So looking at another example, I'm not going to find the domain on this one. I'm just going to simplify it. But the idea here is we have to factor everything And so if I factor this denominator, I get this statement here, and there's nothing that cancels out. So because there's nothing that reduces, okay, this could be a representation of what my answer should be. Now in just in time number 19, we're going to be multiplying and dividing rational expressions. When we are multiplying two rational values, you multiply straight across. Whenever we're dividing, you want to flip the second fraction, and then you turn it into multiplication, and then you multiply straight across. So for this one, because we're multiplying it straight across, we can consider these already combined together. And so I just want to factor everything and then simplify it. So since this is a difference of squares, this factors into a plus 2 and a minus 2. And then this is just 16a, this is 20a squared, and this is just a plus 2. Nothing else factors. Now I can cancel out like factors. So an a plus 2 cancels out, then a plus 2. I have an a squared and an a here. That cancels out. There's a common factor of 4 between both of these, so I have a 4 left over, and that gives me a 5. So on top, I'm going to have 5a times a minus 2, and on the bottom, I'm just going to be left with a 4. And so that's going to be my answer there. Looking at another example, like I said, if we have division, you want to flip the second fraction. And so in flipping that, you get this expression here. And so now that it's been flipped, now you want to factor everything. And so factoring everything, there's a 3x squared in common here. This factors into x minus 2 and x minus 2. So now that everything's factored, you can go through and cancel out things that are in common. So x minus 2, so those are common factors. There's a 3 here and a 3 in common here, so that just gives me a 4 left over. Nothing else reduces, and so I'm going to have x squared times x plus 5 all over 4 times x minus 1. And that right here is going to be my result. Now when we're adding and dividing, there's kind of some steps that we have to keep in line, and I wrote these steps out to kind of help us just a little bit. First, we need to factor the denominator. Then we need to find the common denominator, and then we can add and subtract everything together. So to be able to add and subtract fractions, they have to be common ratios, meaning if we're talking about 1/5, we have to talk about 1/5. So we're talking about 6, we have to talk about 6. If I say I have 1/2 plus a third, even visually that starts getting a little confusing in my brain. But if I say 1/2 plus 3/2, oh, well, that's 4/2. So it becomes much easier for us to combine fractions together when they have that same ratio, or a common ratio there. So to be able to find what that common ratio is, we need to factor the denominator. And so completely factor this, completely factor this. I did that Xbox method here. This was just a factor of 2 in common. So I do have an x minus 1 that's the same, so that keep that in mind. But I didn't have a 2 here, so on this side I need to multiply by 2 over 2. And I didn't have a 2x minus 1, so I need to multiply by 2x minus 1 top and bottom here. So now if we want to take a look, I have an x minus 1 on both. I have this 2x minus 1 in both, and then I have these 2 in both. So now my denominators are exactly the same. So now that they're exactly the same, now I can start adding things together. So on here I can distribute this 2 through. Here I'm eventually going to FOIL. And so if you FOIL all this through, you're going to get this statement here. Combine those together. Okay, I'm going to have to combine these together. The denominator here stays the same. And so combining like terms, 2x squared and 2x squared is 4x squared, minus 8x plus 8x cancel out, and I'm just left with this negative x here. And then 8 and minus 4 give me a plus 4. And so generally this is going to be your answer. Now there are some times you're going to be able to factor that further and see if something cancels out. Sometimes you might going to have to check that. And sometimes you might have to FOIL everything through. And so if I multiply all this back through, you're going to get to this statement. Now, on a test, if I were to give you a test, this would be an appropriate answer if nothing else reduces. My math lab might be a little sensitive, And so because it's a little sensitive, it might want you to put it back into this form. So just know if it's like, hey, wait, I did everything right, what the heck? It might be because you didn't multiply the rest of that through and it wants it in this form. Now when we're subtracting here, once again, I need to factor the denominator. So I factored. Now multiply by what's missing. They both have an x plus 5 in common. So this has an x plus 6, so I need to multiply top and bottom by x plus 6. This has an x minus 4, so I'm going to multiply top and bottom here by x plus 4. Now that they're all the same, okay, now I can distribute this. X times x, x times 4, 5 times x, 5 times 6. Now notice it's minus all of that, so that's why I left it in parentheses. Then distributing that through, combining like terms, and this is one of those scenarios we got to check. Does something cancel out? So if I factor that, okay, this one I was able to factor the top, and so when I factor the top here, that's going to cancel out. And so my final answer could be this. Like I said, my math lab might want you to be able to multiply or FOIL all that through, so just be aware of that. Just in time, number 21, we're going to simplify complex rational expressions. Now, it's going to be very similar to adding what we did in the previous two slides in which we combined these fractions together, but we're going to do it to the numerator and the denominator. So once I do that to the numerator and the denominator, then I can consider this as division. So let's take a look and see how that works. So I have an a down here, I have a b down here. So this needs an a over an a, this needs a b over b, this needs an a plus 3, this needs a b plus, or a cubed and b cubed. And so simplifying that, the denominator stays the same, b plus a, b cubed plus a cubed, and a to the third, b to the third. So now that this is expressed like this, okay, now I can consider this as division, or in this case, all I did was factor that further. Now this is a difference of cubes. Remember, cube root, sum and difference of cubes, cube root. First times first is first. Last times last is last. First times last is in the middle, isn't this a blast? The first sign's from the problem, the second sits reversed. Last time's always positive no matter what the first. Okay, so we just factor that. Now I can look at that as a division. This is saying this divided by this. Okay, that's what that division there says. So it's this divided by this. But division, right, we can turn it into multiplication by flipping it. And so now I can start canceling out like terms. A plus b is the same as b plus a, and ab here, and ab here, so I'm left with a squared and b squared. And so that's going to be my result. Looking at another one. Okay, find the common denominator, find the common denominator, so that needs a y over y, x over x, y over y, x over x. And so now I can combine those together. Once again, this here I can factor it further if I wanted to, or I can, just start writing it as a division like this. And so I can flip it, and so if I flip it there, I can turn it into multiplication. This factors, that's a difference of squares, and so now canceling out like terms, so the x, y's, x plus y's, and so I'm just left with x minus y as my result. Looking at another one, so these are already combined together, so there's nothing extra that you have to do. You can just look at it like this. I factored the top here because that's a difference of squares. And I guess a shortcut way is because we can cancel out, because we know that these, well, if we know that this is going to get flipped, right? This is going to get flipped here, this is going to get flipped here. If you were to write it out, it's kind of like a shortcut way that you can say these values cancel out with these values. Because if we know that this is going to go up to here, and these two are going to go to each other here, the idea is that you can just look at it and you can say, oh, well, this is going to cancel out with this, and this is going to cancel out with this. Now, it's just a shortcut. You don't have to look at it that way. Literally, if that's troublesome, you could write it out and say divided by x minus y over y, and then flip it. and then you could see how the y's will cancel out and x minus y's will cancel out. So it's just however you want to look at it. It's not a big deal. But your answer is going to be x plus y over x. Just in time number 22, simplifying radicals. Example number 1, typically when we do this, we're trying to find the square root, and you want to break it down into its perfect squares. So since 36 is a perfect square, 6 squared, okay, it's going to be 6. Now number 52, notice how when I broke this down, I broke it down into a form of prime factorization. So 5 times 5 times 2. Now when we have a square root, it's saying you need 2 of the same value to make it into a regular multiple, and so a regular factor. So I have 2 5s, so I can bring one of those 5s out and say it's just a 5 times, and then that 2 inside is still a root 2. This one here, sometimes it's easier for us to divide and cancel it out before we actually perform it. So 6 goes into 72 12 times, and now that I have that root 12, now I can reduce it. That 12 is 2 times 2 times 3. And so these 2's here, they're going to be the same, so I can bring one out, and so I get 2 root 3. Now that we've kind of like gone over some of the brief examples that we've talked about in the past here, just to talk about some of these properties. The idea is that if n is even, if my root is even, then if it's written like this, we have to assume that this is always the positive version. So we have to say the absolute value of it. It just creates complexities. When we're multiplying of the same root, you can just multiply them together like so. If n is odd, okay, it is what it is, so it doesn't have to necessarily be a positive. If it was negative, it's negative. If it was positive, it's positive. Just like with an exponent, you can distribute this root. It's not really distributing, okay, it's wrong verbiage, but it's like distributing, where it becomes the root n over root n, the nth root to top and bottom like this. And then if we wanted to, I could look at this as this is the nth root of a to the m, or you take the nth root first and then to the m power. So this one's kind of like you look at the power first and then you take the nth root of all of that. This one is saying, hey, let's do the nth root first, and then you can take it to the power. So sometimes that helps us in reducing if we have to, by looking at it in either of those ways. This next example here, right, if we're able to reduce it, well, in this case nothing reduces, so prime factorization, that 5 means I need to have 5 of the same of these, and so I do, so that's just a regular 2. I have 5 of these, so that's just a regular 3. Now this one right here, because of that negative, there's no real solution here. Now it is going to give you imaginary solution, but if the question's asking us find the real solutions, okay, in this case there's no real solution. Example number 6, okay, I have this negative 5 squared, right, because that's even and that's even, I have to say it's the absolute value of negative 5, which is just going to be 5. So we just have to be aware of that. That's where those properties come in, when that's even and that's even. Example number 7, it doesn't matter how large this is if you just do the prime factorization of this. So the 216 is 2 times 2 times 2 times 3 times 3 times 3. I have 5 x's and I have 3 y's. Since this is the square root, I can look at these in pairs. So I have a pair of 2's, a pair of 3's, 2 pairs of x's, and a pair of y's. So there's my 2, there's my 3, 1 x, next x, and there's my y. And then what I have left inside is a 2, a 3, an x and a y. And so cleaning that up, 2 times 3 is 6, x squared, 2 times 3 is 6, and so that's